This is the video lesson for Mod 3 Lesson 5, Identifying Features of Polynomial Graphs. This lesson is actually a review of something you did back in Math 1 when you talked about features of functions, and then you also saw this a little bit in Math 2. So when we talk about graphs of polynomials, it's basically, taking those trinomials that we did before, like let's say I had here x squared plus 3x plus 4, is really just adding a y equals and turning it into a function, right? So we're going to use all the polynomial operations that we did in the previous sections, but in addition to that, we're going to be graphing, and we're going to see graphs where the degree is larger than 2, right? So the largest exponent is not just going to be 2. We're going to see like 3s and 4s and some other kind of combinations where we have multiple terms. So for a polynomial graph, a few things to kind of keep in mind. So the domain is always going to be all real numbers for these, right? So we're not going to be, closing our domain to make a like enclose like you saw in Math 1. We're not going to have any asymptotes, so we're not going to see like any exponentials or anything like that, like 2 to the x or anything of that nature. And then we're going to find that we're going to talk more about end behavior, which we saw a little bit in Math 1. So basically what happens when it goes to negative infinity. So this is really saying what happens when it goes to the left and when it goes to positive infinity. So what happens when we go to the right? So what's happening with our y value as we go left and as we go right? So we're going to find that we're going to either be answering this question in a couple of different ways. We're either going to be using like positive infinity, negative infinity, and we're not going to see anywhere it's going to like an asymptote or anything like that. We saw this already, but again, the largest degree or largest exponent is called the degree of the polynomial, which we've already been using. One other new piece we're going to see, which is not new for probably you because you saw this in Math 2, but we're going to be using our X-Intercepts. We also call those roots, and essentially that's why we've been practicing factoring. We can find our X-intercepts when an equation is in factored form. So this kind of ties into what we've been doing the past couple of sections. We just haven't been doing it on a graph. So here's an example of a polynomial function that you might come across, right? So it looks like there's a lot going on here. A few things that we kind of notice if we wanted to label this curve, right? You can see that as we go to the left, our graph is going upwards here, and as we go to the right, it's also going to like this positive infinity. Right, so there's actually no there's no maximum because it goes off. So we sometimes call things like relative maximums because there's no the highest it goes is actually infinity. We're also going to see this idea of minimum, which is the lowest parts of the graph. If there is a lowest point, we call that the absolute minimum. So we can have like minimums, that is just when the graph goes low, and then we can have our lowest point, which is the absolute minimum. We can have a relative max, which is where the graph goes higher, but there sometimes is a relative max, sometimes there's not. So like in this first piece, if I was to name a relative minimum, that's where the graph goes low. So the graph goes low at this point right here. Which if I was to name that point, and you can kind of estimate, maybe we'll say it's like negative 2.75, comma, -3. It has another low point that's here, which we maybe would call 1, 0. And then there's another low point that if I go to the right, that maybe I would call this negative 3, maybe 3.5, negative 1.5, or negative 3, or 3.5, negative 1.5. So these would all be considered relative minimums. They're not the lowest part of the graph, but it's just where there's a low point. You didn't really do those in Math 1. I think in Math 1, you only talked about what was like if there was the lowest point. So of these 3 points, the lowest that it is actually this point right here. So the absolute minimum is actually that first point we listed. Okay, so I think in Math 1 you mostly just did absolute, but we kind of like to know where the relative is just so we kind of know what's like happening around that point. For the maximums, well, there actually isn't an absolute maximum because you could see it goes off the graph, right? So it has a relative max, maybe like at these 2 points where it kind of goes high and then goes low again. And so I maybe have a relative max at -1, 4. And then another one at maybe 2.11. I'm just kind of estimating these points here. So those are where the graph goes high and then kind of switches direction. But there isn't an absolute maximum because it goes off the graph. So that's just kind of a little bit of a review from Math 1. What we're really going to see a lot of is talking about zeros. So our zeros are where the graph crosses the x-axis. Okay, so in this case, it actually crosses at quite a few points, or touches at quite a few points. So all of the zeros are going to have a y value of 0. So I have a point at -3, 0. That's one of my zeros. I have a 0 at -2, 0. I have a 0 at 1, 0, and we're going to come back to that one in a moment. Because you can see this 0, it doesn't actually pass through the point. It actually touches that point and bounces back up, which we'll talk about in a minute. And then I have a 0 at 3, 0. Now, when we talk about double zeros are when it simply hits the graph and bounces, but it doesn't pass through. So you can see at 1, 0, it's just touching at that point. It doesn't pass through. So 1, 0 is actually going to be considered, and I'm going to maybe kind of draw this line right here, is actually considered a double zero. So what that means is if I'm counting the number of zeros I have, even though when I physically count it, I only have 1, 2, 3, 4, when this bounce actually counts as a double zero. It actually counts twice, right? So, or we call it a double root, a double zero. So if I was to go ahead and count this, I actually have, I have 1, 2, 3. I would actually count this one twice, 4, 5. So there's actually 5 zeros for this problem. Or you might see it as 5 roots, or as 5 intercepts. Right? So basically, if we were going to name the degree, and we'll kind of see this in a moment, but basically the largest degree, since there's 5 roots, or 5 zeros, this would actually be a degree 5 polynomial. So that means x to the 5th, and then a bunch of other stuff. In this first example, we're just going to look at 2 examples. We're just identifying these different characteristics, and we're going to go into more detail in the next couple sections. But again, a lot of this is maybe stuff that you saw in Math 1 or Math 2. So the first question might be, what are the zeros? Zeros are the same as roots. Right, so we kind of see those called like the same thing. That's also another way of saying what are the x-intercepts. Right? So if I look at this first graph, if I look at all my x-intercepts, I actually have, in this case, there are 4 of them, right? So I have one at -2. I have one, this one right here, you can see is at like a -0.5. I have one right here that's maybe at a 1 and a 3, right? So if I was to list these out, typically we like to list them as like coordinate points. So I might say I have one at -2, 0. It might say one I have at negative 0.50. I have one at 10, and I have one at 30. If I look at all these roots, the graph actually passes through these points. It doesn't necessarily hit the point and bounce back, so there aren't any double roots. So if I count the number of intercepts I have, in this case, I have 1, 2, 3, 4. So the least degree that this could possibly be is a degree 4, because there are 4 roots here. And there was no double roots where I had to count it more than once. So the minimums here, I actually have 2 minimums, but I only have 1 absolute minimum, right? So I actually have these 2 minimums here. I might just list the absolute for both these, because that's probably where we're going to see that come up a little bit more. So my absolute minimum, I have one at maybe 2.1 negative 4. That's the lowest point on the graph, and that's an absolute one. So I'll just list my absolutes. My maximum, I have a maximum that is at about 0.5, 1.25, somewhere around there. I don't have an absolute maximum, so I might list this just this one that's here. But I'm going to write here that there's no absolute maximum, because it goes off to infinity. So the highest point I find, I could still find a point that's higher. For my domain, it's a polynomial, so it's going to be all real numbers. My range is, remember, it goes low to high. So my lowest point is right here. We said again, it was I said 2.1, negative 4. My highest point goes to infinity. So if I look at for my range, it goes, my lowest is negative 4. My highest is infinity. And I would use a bracket for the negative 4 because it hits that point, but then I obviously don't use a bracket for infinity. End behavior is the one that's always a little tricky, right? So basically what end behavior means, you're going to write it that as x goes to negative infinity. Actually, I'm going to move this down to the bottom. Give myself a little more space. So as x goes to negative infinity, and as x goes to positive infinity, what's happening to the y value? Okay, so this is basically saying when we go to the left and when we go to the right, what's happening, right? So in this case, I have 2 arrows going here. You can see these are both going to positive infinity. So this one's actually kind of an easy one. When I go to if I follow the graph to the left, it's going to positive infinity. If I follow the graph to the right, it's also going to positive infinity. So my end behavior, it's actually going in the same direction for left and right. And then finally, increasing and decreasing intervals. If we look at this, it's basically when is it getting going up in a positive direction or going down. So if I label my graph, and I'm going to label this point right here. And then it's always kind of good to label those max and mins when you're doing increasing and decreasing. Okay, so I got those 3 here. Awesome. So when we go ahead and talk about increasing and decreasing, you always go from left to right. And so I'm going to go to the left. I can see that as I'm going to the left, in this first interval, I'm actually going downwards. So this would be a decreasing. And then I would see then from at this interval, when I go back up, this is increasing. When I go in the other direction, this is decreasing. And then when I go back up, I'm increasing. So again, I'm just going from left to right. And when I'm going up or down the graph. So my increasing intervals, you're always using the x values, right? So when I write this interval out, my increasing I see from negative 1.5 to 0.5. I'm increasing, and then at 2.1, 2, and then it goes up to infinity. Is when I'm increasing, right? And again, we're just listing our x values. For decreasing, well, if I go to this side here, that's negative infinity because I'm going to the left. So, and again, we're talking about x value, not the y value. That's why it's not positive, because you're going to the left. So from negative infinity to negative 1.5, I'm decreasing. And then from 0.5 to like 2.1, I'm decreasing. In this last example, this one is going to go a little bit faster, but again, it's the same process. So zeros are our x-intercepts, right? So if I look at my x-intercepts, in this case, it looks like I have 4, but I actually have technically a double root at 1, 0 because it doesn't pass through. So in this case, when I list it, I'm only going to list the 4, but I might indicate in some way, so when I have to answer the second question, that one of those is actually a double root. So I'm going to put a little dr next to that 1, 0. So when we write our least degree, even though there's only 4, I'm going to count that double root twice. So my least degree is actually going to be a 5. When we talk about our minimums and maximums, I'm just going to list these out here. So our minimums, and I'm going to kind of estimate, I might say this is like a negative 0.5, negative 2. And I have another minimum at, what is that, about a negative, I'm going to say maybe 3.2. And then like 6.1. Negative 6.1. So I actually have 2 minimums. I don't have an absolute minimum though, because you could see the arrows go to negative and positive infinity. And then for my maximum, I don't have an absolute max, but I'm still going to list it. So I can do my increasing and decreasing intervals. So I'm going to say this is about negative 2.5 and 1, and this is the 1, 0. So for our minimums, we can just simply list all those out. And then same for the maximums. For our domain, it's a polynomial, so it's all real numbers. And our range, it actually goes off the grid in both directions, so it's also all real numbers. For the intervals, I'm going to write that, and then we'll come back to the end behavior. So the intervals for increasing and for decreasing. For my increasing, when I go from left to right, you can see that as I go, and I always start from the left. In this first interval, I'm actually increasing. And so this would be from negative infinity to negative 2.5. And I'll write that with the regular marker here. And when we name our intervals, we're always using parentheses, and we're always just listing the x values. So I'm not listing the y values in any way. For the next interval, you can see from negative 2.5 to negative 0.5, I'm actually going downwards. That's decreasing. So I'm going to write on negative 2.5. to negative 0.5, I'm decreasing. When I go to the next part of the graph, you can see I'm actually increasing again. So that would be from negative 0.5 to 1. And then finally for our last part, or we're almost there, we got actually 2 little parts left. We're actually decreasing again from 1 to 3.2. And then finally, in our last piece, which is right here, from 3.2 to positive infinity, so because it goes off the graph in the right direction, we would say that we're increasing. For end behavior, that's a little bit different. We're looking at what happens when we go to the left and what happens when we go to the right for what happening with y. So when I go, it always starts off the same as x goes to negative infinity or x goes to positive infinity. What's happening to f of x? And as x goes to negative infinity, you can see when I go to negative infinity, it's going downwards. And then for this one, when I go up to, to the right, it's going to go upwards. So this would be negative infinity and infinity. If you have any questions, you can sign up for T-Bolt time, get help in the center, or ask questions during class.